Hey everybody, this is Larry. This is day 15. Alright, to March. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this poem. Yesterday was Pi Day. I forgot to mention it because I was just so fuzzled. Go Pi Day, especially for math nerds here. I mean, maybe you, maybe not, but definitely this guy. So yeah. Yeah, I just went to the gym. I did squats. I finally did 2 plates, 225. Feeling pretty okay, but feeling so tired. I actually took a nap and I still feel so tired. Maybe just getting old. And hopefully I'm gonna run like at least 6 miles tomorrow. I don't know how long I'm gonna end up going, but yeah. But yeah, today let's take a look at today's poem because I don't know why did I say it like that. Today, look at today's poem. Anyway, we have 2560 House Robber 4. Let's go. There are several consecutive houses along the street, each of which has some money inside. There is also a robber who wants to steal money from the homes, but he refuses to steal from adjacent homes. Okay, so far so good. Capacity of the robber is the maximum amount of money he steals from one house of all the houses he robbed. You're given an integer nums representing how much money is stashed in each house. Okay. You're also given an integer k, which represents the minimum number of houses the robber will steal from. It's always possible to steal at least k houses. I thought I missed the word reading, but I guess they missed the word. I mean, stealing houses would be pretty intense, but yeah. Return the minimum capability of the robber out of all the possible ways to steal at least k houses. Come on, man. Steal houses. Okay. Anyway. It's almost like it was written by Google Translate or something. I don't know. But anyway, okay. So what does this mean, right? What are we trying to do? Minimum capability. The naming of these things are very awkward. That's why I'm like having a second pause. The capability is the maximum number you steal from one houses. Okay, so my understanding for now, and maybe it's wrong because this is very awkwardly phrased in general, is that you do not steal from adjacent houses. You want to steal from K houses, and you want to minimize. You want to minimize this. You want to minimize the max that you steal from one house, right? Okay. I think there are a couple principles here, right? I think one thing that you, and of course, let me make sure that I'm on screen because I didn't do it yesterday. So even I thought I checked earlier as well, but now I'm just a little bit paranoid. But I want to say that, one part of it is that honestly, it is yesterday and the day before are binary searches, right? So it's a little bit of a spoiler, honestly, for me, because I don't know. It's kind of tough to figure out why I've gotten it. I probably would have gotten it maybe a little bit slower, but knowing that it's not even a hint, but it's just like, the theme makes it a little bit easier to at least figure out binary search, right? I'm not gonna lie there. And a core part about this is, well, so I get a question a lot about how do we identify binary search problems. And honestly, and I even got a comment the other day where they were like, "Oh, there's no way anyone can do it this fast. He definitely have seen it before. So that's the only way he could have done it so fast." Which one, I think is a compliment because no, I don't. And two, it's like I think it's a compliment because we're like, "Oh, he can't possibly be doing it for real. He must be cheating or something like that, right?" I don't know. But I also just don't generally remember these, especially binary search problems, because honestly, they all kind of looked similar at a certain point. But I would say, to answer the actual question of how do you recognize this as a binary search problem, honestly, for me, I don't necessarily. I think there is this tendency to do this pattern matching thing that people do, or claim to do anyway. I don't know that I do it per se. I mean, I'm sure there is some level in the back of my head somewhere, but I don't go around and be like, I think I don't always necessarily, like, I don't need a pattern or some sort of hint to say that is a binary search. What I do instead is that I just guess, right? It's almost like actually, now that I talk about it, it reminds me of like doing integrations, and sometimes you just guess, right? Like you guess and then you see if you derive it is the integration that you got, right? But in this case, excuse me, let me drink some water. I feel like I have some very spicy mapo tofu, and I think like, I don't know. And what I mean by guess is just that, okay. and the speed at which you do this gets faster over time, right? But sometimes I'm just like, okay, I don't know what it is, so then I'll be like, okay, what if this is binary search? If this is binary search, can I figure out how to solve it? And that's it. The answer may be no, and if it's no, then I go, okay, well, it's a dynamic program or something like that, right? But yeah, that's really only that's the idea of how I come up, or I check whether it's binary search. And sometimes that check is fast, sometimes that check is long, sometimes I write it and then I'm like, oh wait, this is not binary search because I missed some monotonicity thing, right? But this one, so again, it is going to be similar to, I think yesterday or the day before, maybe both, I forget which. People say I seen it before and I just memorize it, but I don't even remember what. I mean, I do remember that they're binary search, but I honestly do not remember yesterday's problem or the day before, unless I get like a little bit of hint or something. So I don't know. If you ask me, they're not that memorable. It's like at this point I have like 4,000 videos or something on YouTube, right? It's like, can you name 4,000 of you? Like, can you remember 4,000 people's name? I can't. I could bet. I don't. Right. So yeah. Anyway. What was I saying about binary search? But yeah. I think the idea here is that, okay, let me just try if there's a binary search, right? I go, okay, well, if there was a binary search, how would I go? I mean, this is obviously not a searching an array thing. It is searching in an answer thing, right? Why is it obvious? I don't know. It's just that there's nothing to do with the array. It is, but it's just that if you're given an answer, can I check whether this answer is correct or not, right? I think that's it. That's basically how I think about it. And of course, like I said, there's also some sort of monotonicity, right? Meaning that you want an answer that goes yes, 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 and then at a certain point goes no. Then after that point, it's all no, right? So yes, 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 no, 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 or the other way around. Doesn't matter, right? Excuse me. No, 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 and then yes, 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 right? So you're hoping to find that, right? That's the only criteria that I have, right? Is for that, and for the answer, it kind of makes sense because I don't know. And the reason why the answer comes up a lot, or like binary searching for the answer, maybe I don't know how often it comes up, but it's just that it is very easy, and in terms of complexity, right? Like I don't have to analyze complexity usually that much, because even for in this case it's 10 to the 9, but it almost doesn't even matter, right? Because if it's 10 to the 18, is you, instead of doing 30 iterations, you do 60 iterations of a binary search. Binary search scales incredibly well, so it's not quite linear, and sometimes you do have to pay attention, especially if you do like log square n stuff. But for this, but for like these kind of binary search problems, I don't think about the complexity, right? And then the question is, how can you do the check of this? Okay, let's say we have an answer X as the quote-unquote capability. What does that mean? Well, you might have to read it again, because I'm reading it again because I don't remember the problem anymore. But okay, so capability is just the max amount of money, right? That means that given a capability X, every house that you steal from has to be equal to or less than X, right? That's the only thing, and that you can do with a linear scan. There is an additional wrinkle, if you will, right, which is that adjacent homes. And for that, you can do greedy. That would be my first intuition. But intuition for greedy is not always enough. But there is a easy-ish, at least to me, proof, right? The proof is just kind of more of a state thing, right? Let's say you have A, B, and C, and they're all equal for this purpose. And then the question is just that if you could steal from A or B, well, what does that mean, right? Well, it just means that you always want to steal from A. And the reason why is because then now you just have more degree of freedom in the future, right? Because then now if you steal from A, if you want to think of it kind of like, then now you have all this stuff. And if you steal from B, you have all this stuff to choose from, where the capability is still, or capability is going to be the same anyway, but you have now K-1 houses, right? And from a greedy kind of point of, I think I messed up this actually, because you have stealing from A means that you cannot steal from B, right? So this is choices, and stealing from B means that you, I don't know, you start from D, I suppose. And I just say, and I say that they're all equal because it makes it even more obvious in the quote unquote kind of like the worst case scenario, right? But in here, this is a superset of this, right? So meaning that this just gives us strictly more choices. So in that case, so it's a very easy proof in that, like, it's almost like the equivalent of saying, I'm going to give you, you can choose whether I give you $5 or $6. And then you're like, well, look, listen, $6 is strictly better than $5. And like, you could say it's greedy, you could say it's intuition, but like, it's a very easy map, right? And nothing else changes about the state of the world. Then you just normally just take the one that's more. And it's just like a very easy thing. Maybe that's not a strict proof though, but yeah. For a strict proof, you probably could do some like exchange type thing, assuming the values of C and D, and then do the math on like 4 elements or something. But yeah, right? Anyway, so that's basically it. Yeah, and then now let's do the binary search. We start the bounds. The left side we have, so you can always do it. So it's not going to ever be 0, but it also doesn't matter. It could be 1, but I think in this case 0 doesn't give you any issues, so 0 and 1 doesn't matter. And then we're on the right side. What's the maximum thing, right? The maximum is just going to be the max of one element, right? So that's going to be 10 to the 9, or maybe we can just write also max of nums for loss of generality. Right? So yeah, so then this is just standard binary search things. If I could get it out. Okay, so at this point, I always pause because it depends on what function I want to write, right? So we have the target. Like, I feel like people always write out the template, but it doesn't. It really just depends on how the function, this function, and for me, how I write this determines how I write the rest of this. And I want to write this in the way that is the easiest to write, right? And for me, for this good function, I want to write, yeah, can we steal from at least K houses, as where the max the capability, which is the max really, right? So the max is target, right? And that's it, right? So then now we have maybe I didn't need it. How do I want to write it, right? So count equals 0. I mean, for now we don't even have to implement it, and then, but the thing is that if this is true, what happens? So if this is true, what happens? If this is true, we want to try a smaller number, right? And because mid is ratted, then we want to say right is equal to mid because inclusive bounds, right? Otherwise, then left has to be mid plus 1. And the reason why is mid plus 1 is just because, well, mid cannot be true. So you want to skip mid, and you want to also try a bigger number because a bigger number will allow us to try it. And that's it for this part. But then now we have to implement this, right? So here we have maybe say count equals 0. And then we have, I don't know, let's just say we have skip is equal to force, right? So we have 4x in nums. If skip, then we set skip is equal to force, and then we just skip. Otherwise, if x is less than or equal to target, skip is equal to true, right? And that's it. unless I mess something up, which is, I don't know, frankly, happened a lot. But yeah, that's all I have for this one. Yeah, what's the complexity, right? Well, this is still going to be O of R, of log of R, where R is the range of the numbers. That's how I want to say it. You should say B for bits or something. But yeah, and that is just determined by the max number, right? And this is going to be log of R of that. And this is linear. You can see the linearness, hopefully. And that's it. O of n log R, and that's all I have for this one. Let me know what you think. Thanks for watching. Have a great weekend, everybody. Stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye-bye.